And welcome back, Avon High School ACE College Algebra 2 students, for this, our third video in the series of our section 13.4, covering the ellipses. This video is going to take a look at what I believe to be is page 3 of your notes um, that deals with example 2, and it has 3 parts, so we're going to run through all 3 parts of this. So the directions say that you are to graph the ellipse defined by each equation below, and we are then to proceed with identifying and labeling the coordinates for just the foci. Because as we've talked about in the other videos, the foci are the points that are going to be a little bit more challenging for us to find. So first thing that we notice in example 2, part A, is that we have the wonderful sort of standard form, if you will, for this particular ellipse. It has the center very recognizable, and from there we can find out a lot of other pertinent information. So we're going to go ahead and find the center, -2, -3. There's really no need to write that down per se. We can just graph it. And then it doesn't matter which of the two numbers you look at first, you just have to make sure you kind of use them in the right way. So remember that the number that's underneath the x part of the fraction, his square root, which in this case is 3, will dictate how far you go out in the horizontal direction from your center. So we go out 3 units each way. The value that's underneath the y, excuse me, the y fraction, 5, the square root of 5 would be, 25 would be 5. So we would count out 1, 2, 3, 4, 5. I'll say that again. We take the square root of 25 and get 5. And that's how far we would count out in the y direction. Now, when it comes time to sketch the actual ellipse, you are going to have to freehand it. You want to try to do as good of a job as you can. What I want you to avoid, I always have my students try to avoid making the dreaded diamond shape. You don't really want to graph something like that because it's not a diamond. So what you can do is just try to do the top half, make it somewhat nice and smooth and curved, elliptical, and we'll do the same for the bottom. Of course, it's going to be hard to make it perfect, and that's fine. It's not an art class. Strive to make this the elliptical shape as best as you can. So we've taken care of the graphing part. Now we have to find the foci part. And if you recall, there is a wonderful formula that we can use to find the foci. And that formula is basically taking the smaller of these two values square root squared, which in this case would be the value 9. So to kind of like put that into a little bit better perspective, we're going to take this distance right here. We're going to take that short distance, that half of the minor axis distance, and we're going to square it because we're using the Pythagorean theorem. And then we're going to add to that the distance that takes us all the way up to where the foci would be, which I'm going to have to guesstimate where the foci is going to be. Maybe it's going to be right around in this vicinity. But that's going to be the value f. We call f the distance from the center to that focus point. And then if you remember, we normally would set that equal to the square of the hypotenuse. But as we've discovered before, that this square of the hypotenuse, or this length I should say, is always going to be the same as half of that major axis. Every time that seems to work out. So, I'm going to move this guy back to where it was. So, we can set this equal to, in this case, 5 squared. So if we solve for f, we would get 25 minus 9 being our f squared, which makes f squared equal to 16. And that does give us an f value of 4, which this is kind of an unusual problem in that it does have some very, very nice integer value coordinates for its foci. So to finish this up then, we know that 4 is the distance we would count out from our center to get to our foci. Now you have to know which coordinate point that you're going to add the 4 to. And because the major axis here is vertical, we are going to add this 4 to the y coordinates of the center. So if you remember, the center, I'm going to write it here just so that we can relate to it. The center was -2, -3. The foci points are going to be at these two spots. Right? We said 4 units from the center. So to find those, we would lock in our x-coordinate. He would not change, but we would add we would add 4 to the y value. And then we would do the same thing, but then subtract 4, and in this case get -7. And there we have the coordinates of our two foci. Now, we have to understand that that's going to be very rare. Normally your foci are going to be some pretty nasty, irrational expressions that probably have square roots over them. Let's go ahead and take a look at part B. In part B, we will find that our center is at +1, 0. So we can begin with that. And I might even write down what the center is over here so that we can relate to it later. In the x direction, we're going to count out 1, 2, 3, 4 units. 1, 2, 3, 4 units. And in the y direction, we're going to count up 1, 2, 3 units. And 1, 2, 3 units. So we are now ready to connect the dots and sketch our ellipse. So the top half might look a little something like that, maybe, and the bottom half might look a little something like that. Okay, now we come up to our foci now, and we once again will use the same formula. You would take essentially the smaller number of your two denominators, because that's always going to be half of your minor axis squared. So you just take that smaller number, and then you would add f squared and set it equal to the larger number. Now, sometimes I don't like teaching it that way. I don't like just blindly saying small number plus f squared equals big number, but I want you to know that that will work. But I also want you to realize that you're using the Pythagorean theorem in the exact same way that I demonstrated it in part A. So in this particular case, f squared is going to equal 7. So when you take the square root of both sides, we're going to get really plus or minus the square root of 7. And if I were to go back just a moment, I probably should have put the plus or minus here in front of the 4. I mean, we still use that idea about adding 4 and subtracting 4, but that plus or minus will probably make it a little bit more prominent. So it now comes time to render our foci. And the first decision that you're going to have to make is which coordinate, the x or the y, is locked in. Well, we know that the foci in this problem has to lie along this major axis, which also is the x-axis. Remember that your foci are always on the major axis. So the y value is going to be 0. So the y value is the one that's not going to change. So I'm just going to lock 0 in. But it's the x-coordinate that's going to change, right? We're going to start at 1, but we're going to add something to it, and we're going to subtract something from it. That something is the square root of 7. So we would add the square root of 7, and then we would subtract the square root of 7. And that would give us these 2 points. Now, the square root of 7 is a number that's, it's about 2 and some change, a little bit bigger than 2.5 maybe. So that would probably put the foci somewhere around here, yeah, and maybe somewhere around there. All right, take a look at our last part of this example. In part C here, we have a little bit more work to do because we don't have the standard form for our ellipse. So we are going to have to complete the square, much like we did with the circles. The only exception, we've got some numbers in front of our squared terms that we're not maybe real thrilled that they're there. So the first thing that I'm going to say is to go ahead, as we did before, and group your x terms together. I'm going to go ahead and leave a little space and group the y terms together. If the term has neither an x or a y, like the 16, we'll move it over to the other side, so we would subtract it. Now, it's very important that we all understand that we cannot complete the square as long as we have numbers in front of our squared terms besides 1. Those coefficients, 4 and 9, have to be taken care of. We have to strive to get 1 as our coefficient. To make that happen, you're just going to do some factoring. 4 easily factors out of 4 and 16. That will typically be the case. So I'm going to factor out of 4. Now, leave your space before you close off your parenthesis. Do the same thing here, factoring out of 9. Leave some space. Close out your parenthesis. Now we can go ahead and do our process of completing the square. In the first case, for the x's, we have 4 cut in half is 2, squared is 4. So we are going to add 4 right here. But remember, whatever you do to one side of the equation, you have to do to the other side. Now, did we really add 4 to the left side of the equation? No, we actually added a 16 because of the 4 that's factored out. So the 16 that we've introduced to the left side of the equation must also be added to the right side of the equation. We'll do very similar work with the y completing the square process. Our linear coefficient is -4. Cut him in half, we have -2. Square, we have +4. So again, we're going to add 4 right here, but is it really a 4? Nope, it's a 36. So we would need to add 36 over to the right side. Now things really start to fall into place. You're going to use your idea of the factoring of a perfect square, binomial square, and that works in both cases. Remember, if you're really lousy at factoring, which at this level you shouldn't be, but if it's a problem, you know that you can always rely on those two values to give you these two results. It's a little trick there that works. So on the right side of the equation, we see that the 16s will cancel and we have 36. So we're not quite where we want to be yet. The standard form of an ellipse always has this very common look to it. And if I scroll back up and refer to A and B, what do we notice is always on the right side of the equation? A 1. You want that to happen. That's going to make our lives a lot easier. So we want this 36 to become a 1, and the easy way to do that would be to divide every single term in your equation by 36. That's going to cause some reducing over here to get x plus 2 squared over 9, and then add y minus 2 squared over 4, and now we have our 1. And if you look at this problem now, it looks very similar to the ones that were presented to you originally in example 2, parts A and B. So we're going to go ahead and find our center, which is at -2, +2. It's right up here. I'm going to go ahead and write that down here in case I need it. And we're going to count out 3 units in the x direction, 3 units in the y direction, 3 units in the x directions, 2 units. I will count out 2 units in the y direction. So this is a much smaller ellipse. I'm going to go ahead and connect the dots as best we can. And then the only thing left for us to do is to identify the foci. So again, we're going to rely on our formula. Our formula says take the smaller of these two values, 4, add it to f squared, and set that equal to the larger of those two values, 9. So as you can see, f squared will be 5, which makes our f the square root of 5 plus or minus. So remember, f is the distance your foci are from the center. But you also have to remember, are your foci going to be along this horizontal, or are they going to be along the vertical axes? And the answer would be the horizontal, because it is the major axis. You always have to pick the larger of the two. One of them is always going to be larger, because let's face it, if they were the same, you would have a circle. So we're going to take one of our coordinates and lock it in. Well, that coordinate that we're going to lock in is going to be the y coordinate. It's not going to change because it's the same along that horizontal line. So 2 will lock itself in. And then for the x coordinate, we'll start with -2. That's where our center is. But we will add the square root of 5. And then we would subtract the square root of 5. And now you've got your foci here. All right, anyway, I hope this helps. We're going to have one more video that addresses example 3, or at least parts of example 3. And I'd like to show a little bit of calculator usage, especially with the TI Inspire and its wonderful conic section interface. So anyhow, I hope this helps, and we'll see you next time.